In this video, we're going to look at another application of integration by parts. Here we have integral x times e to the x squared times cosine of x squared integrated with respect to x. You can see how we have a product of three different types of functions. We have polynomial, that is x, we have an exponential function, that's e to the x squared, and we have a trig function, that is cosine of x squared. And whenever you have a product of three different types of functions, and a good technique is integration by parts, because integration by parts is really the reverse of the product rule. So if you have a product of functions and substitution technique does not work, we will apply integration by parts. We're going to let u be equal to e to the x squared. Its derivative du is equal to e to the x squared times 2x dx, applying the chain rule, differentiating the exponent. dv is what is left over. dv is equal to x cosine of x squared dx. And if you integrate both sides, we can apply the substitution technique using t is equal to x squared and differentiate that to get dt is equal to 2x dx, divide by 2, you get 1/2 dt is equal to x dx. And if we carry out this integration, we will get v is equal to sine of x squared divided by 2. Let's put this in a box. Alright, so what we have is u times v. We're going to apply the integration by parts formula. Integral u dv is equal to uv minus integral v du. So we have u times v, that's going to be e to the x squared, times v, that's sine of x squared, divided by 2, minus integral v, that's sine of x squared, divided by 2, times du, that's going to be e to the x squared, times 2x dx. We can see how the 2 cancels out, and we will get e to the x squared, sine of x squared, divided by 2, minus integral x, e to the x squared, sine of x squared, dx. Now, you can see how we started with the integral x e to the x squared times cosine of x squared dx, and now we have another integral that looks very similar. So that means we have to integrate by parts again. Alright, so what we have is integral x e to the x squared times cosine of x squared dx is equal to 1/2 e to the x squared sine of x squared minus integral x times e to the x squared times sine of x squared dx. We're going to apply integration by parts again, and we're going to solve this integral. Integral x e to the x squared sine of x squared dx. We're going to make the same choice for u. So we will let u be equal to e to the x squared. Its derivative du will be e to the x squared times the derivative of the exponent, that's 2x dx, and dv will be what is left over, which is x sine of x squared dx, and we integrate both sides to get v. v is equal to minus cosine of x squared divided by 2. Now, to show this step, how to obtain v, we actually have to do a substitution technique by letting t be equal to x squared, and dt is equal to 2x dx divided by 2, and you get 1/2 dt is equal to x dx. So that's the substitution method just to obtain v. Alright, because that's easy, I've left that for you to do on your own. Alright, so now let's apply the formula. Let's apply the integration by parts formula. So we have u times v, and that's going to be e to the x squared, times v, which is negative cos of x squared, divided by 2, minus integral v, which is minus cos of x squared, divided by 2, times du, which is e to the x squared, times 2x dx. All right, so what are we going to do? Well, let's simplify this a little bit, and we get negative 1/2 e to the x squared cosine of x squared, and the 2 cancels out. We get plus integral x e to the x squared cosine of x squared dx. Now we can see that the integral that we were looking for, which is this part here, integral x e to the x squared times cosine of x squared dx, that integral has reappeared. This is the recursive nature of the problem. So you can see now we can solve this. So we had I is equal to integral x e to the x squared times cos of x squared dx. That's equal to 1/2 e to the x squared times sin of x squared minus integral x e to the x squared times sin of x squared dx. And we integrated this part again, we integrated that, applying integration by parts, and we got negative 1/2 e to the x squared times cosine of x squared plus integral x times e to the x squared times cosine of x squared dx. So what we were seeking has reappeared. And now we just have to organize the answer, solve for the unknown integral. So what we have is I is equal to 1/2 e to the x squared sine of x squared minus minus bracket negative 1/2 e to the x squared cosine of x squared plus I. Let's distribute the negative 1 and remove the brackets. We get I is equal to 1/2 e to the x squared sine of x squared plus 1/2 e to the x squared cosine of x squared minus I. Now bring I over to the other side and we get 2I is equal to 1/2 e to the x squared sine of x squared plus 1/2 e to the x squared times cosine of x squared. Divide by 2, divide by 2, and we're going to, of course, add a constant c. So you get I is equal to 1/2. Actually, let's just do the algebra. We get 1/4 dividing by 2, 1/2 divided by 2, 1/4 e to the x squared sine of x squared plus 1/4 e to the x squared cosine of x squared plus c. This is the answer. This is the answer to the integral. So what we have basically done, let's do a review of the strategy that we applied. We basically applied integration by parts. We let u be equal to e to the x squared and dv is equal to x times cosine of x squared dx. We label the integral as I so that when this integral reappears, we can algebraically solve for it. So the integral x e to the x squared times cos of x squared dx, we integrate by parts once to get 1/2 e to the x squared sine of x squared minus bracket negative 1/2 e to the x squared times cos of x squared plus another integral plus integral x e to the x squared cos of x squared dx. But now you can see that the integral that we were seeking has reappeared. And this is a recursive or loopy nature of this type of question. So we have on the left-hand side, we have I is equal to 1/2 e to the x squared times sine of x squared plus 1/2 e to the x squared times cos of x squared minus I. You can bring the I over and solve for I. And if you do that, you will get this result here. This is the answer to the integral. All right, thanks.